All right, hello everyone. Welcome to my channel. I do educational videos on this channel on many different subjects, but we've been locked in for a long time here on the reciprocal system of theory. I think today is video number 196. And the reciprocal system of theory is a theory of everything, a grand unified theory, a cosmology from Dewey B. Larson. And he rolled this out in the 20th century up until his death in about 1990. We are actually looking at his 1979 book called Nothing But Motion. And we're in chapter 14 of that book called Cosmic Elements. Now, I apologize for yesterday. My phone just overheated and it just shut off in the middle of a sentence in the last minute of the video. So I just left it be. I had a couple of things going on, and my phone was too hot to do a retake. So we're going to start right where we left off, or we'll start that paragraph over again when we get started. Just a quick rundown of the reciprocal system. The basic idea is that we live in a universe of motion. This universe is a universe of motion. It's not a universe of matter. It's not a universe of energy. It's a universe of motion. And matter and energy are merely two different varieties of motion. Motion is actually all of our scientific quantities are merely forms of motion. And for Larson, motion was the relationship between space and time. Now we see that in the most basic, our most basic understanding of motion is speed. The car is moving 20 miles per hour, 20 miles of space in 1 hour of time, space over time. Now it gets more complicated than that because in Larson's first postulate, he has two fundamental postulates from which he derives an entire theoretical universe. And in his first postulate, he says that both space and time have their coordinate aspects, meaning that they have three or more dimensions. And so space we recognize generally as having three dimensions or more. And time also has three dimensions or more, which we don't generally recognize. So that makes the relationship between space and time a little bit more complicated because time can be multidimensional as well as space. So speed is a simple kind of motion, time over space, but or space over time. But for example, matter in Larson's formulation is time to the third power over space to the third power. So there's multiple dimensions that you enter into a relationship between space and time, or a kind of motion. So matter is a kind of motion. It's a relationship between space and time, but space and time in this case have multi-dimensions. Then space and time also have their scalar aspects, which is really one dimension of scalar motion. Now, Larson eventually makes clear that three dimensions of space, every dimension of scalar motion encompasses three dimensions of space or time. And a scalar motion is a motion that has a magnitude, but it does not have a direction, or it has every direction. And you can envision this by taking your magic marker, putting a bunch of dots on a balloon. If you blow up the balloon, all the dots are moving away from each other. That is an outward scalar motion. Then you suck in the balloon, and all the dots are moving toward each other. That is an inward scalar motion. There is a magnitude, a speed of that motion, but there is no direction. There's no specific direction. So that is another aspect of both space and time. They have their what Larson calls clock aspects, clock time and clock space. We recognize that in time, clock time. The clock is always getting later and later and later and later. But in the same way, space is always getting farther and farther and farther apart. These are both one-dimensional scalar motions. And again, that one dimension of scalar motion encompasses 3 dimensions of vectorial motion, the coordinate kind of motion. Then also time and space both come in only discrete units. There is no continuity of space or time. They both come in chunks, very small chunks that we probably cannot resolve as being individual, but they do only come in chunks. And when you have exactly 1 unit of space in 1 unit of time, you actually have the speed of light. So the speed of light is what Larson calls unit speed. And unlike Einstein, who says that the speed of light is the maximum speed of the universe, Larson says that the speed of light is the midpoint of the universe. And there's an entire half of the universe that Larson calls the cosmic sector that is actually moving faster than the speed of light, as well as the half that we're familiar with, called the material sector, that is moving slower than the speed of light. In the material sector, we have coordinate space, 3-dimensional space, and clock time, progressing time. We are familiar with that. But in the cosmic sector, the roles of space and time are reversed. And so in the cosmic sector, we have 3-dimensional time and clock space. Space is always getting farther and farther apart. And we have a 3-dimensional time. And so that kind of extrapolation works in general, so that even though we don't know anything about the cosmic sector, we can't see the cosmic sector, we know everything about it because we can extrapolate from the material sector. We have observed and measured the material sector, and all we have to do to convert or extrapolate to the cosmic sector is reverse the roles of space and time. So, okay, now we are in his chapter called Cosmic Elements. So he's, we went through the elements, the material elements, your material hydrogen and your material helium and lithium, beryllium, and so on. And those were combinations of motions. So, for example, oxygen, element number 8, is 2 primary 2-dimensional magnetic rotations. It is 2 secondary 2-dimensional rotations, and it is 2 negative 1-dimensional rotations. So that is Larson's notation, A, B, C. A dash B dash C is the 3 numbers that Larson uses to delineate the periodic table, or the elements of the periodic table. So that's how he maps it out. And so in the same way, in the cosmic sector, he's now developing what the atomic constituents of the cosmic sector look like. What is cosmic oxygen? Well, I would say naturally it's the same, 2-2-2, but instead it's based in the cosmic sector instead of the material sector. And those motions are in space rather than being in time, or they're in time rather than being in space. Okay, so we're going to take over here in the middle of this paragraph, or in the middle, at the beginning of this paragraph that I left off in last time. Okay, furthermore, gravitation in the cosmic sector acts in time rather than in space, and the atoms of which a cosmic aggregate is composed are contiguous in time, but widely dispersed in space. Thus, even the relatively small number of cosmic aggregates that we do encounter in our movement through time are not encountered as spatial aggregates. They are encountered as individual atoms widely dispersed in space. We cannot recognize a cosmic star or galaxy because we observe it only one atom at a time. Radiation from the cosmic aggregate is similarly dispersed. Such radiation is continually reaching us, but as we observe it, this radiation originates from individual, widely scattered atoms rather than from localized aggregates, and it is therefore isotropic from our viewpoint. This radiation can no doubt be equated with the black body radiation currently attributed to the remnants of the Big Bang. Okay, just to let you know, isotropic means that it's kind of equally balanced in all directions. And the other word there would be non-local. So this is a term that Larson uses in conjunction or similar as a synonym to widely dispersed. So if something is localized, you can see where it's coming from. But where it is non-local, that means that it is widely dispersed in all directions. So this is the phenomenon that Larson is talking about, black body radiation. This is a radiation that's coming from all directions equally. And so that's how we observe something from time, because a direction in time is not a direction in space. It is analogous to a direction in space, but it is not a direction in space. So if we are going to view something in time, we're going to see it as being dispersed in all directions. So that's a way that when we are observing from our material sector, again, we see space, we do not see time. When we see time, we only see time in the way that it affects space. And it affects space in this inverse manner. We were going over the white dwarf star yesterday. We see a white dwarf star is an exploding star exploding faster than the speed of light. When it crosses the speed of light boundary, then we see it as an explosion in time. But we do not see time. We see only space. So we see a white dwarf star as an implosion in space, the inverse. It's exploding in time. We see it as an implosion in space. Okay, next paragraph. All of the somewhat sensational suggestions as to the existence of observable stars and galaxies of antimatter and the possible consequences of interaction between these aggregates and bodies composed of ordinary matter are thus without foundation. The antimatter fuel generators which supply the energy for space travel in science fiction will have to remain on the science fiction shelves. The difference between a cosmic star and a white dwarf star should be noted particularly. Both are on the time side of the dividing line so far as the translational speed is concerned. That is, both are composed of matter that is moving faster than the speed of light. But the white dwarf star is otherwise no different from the ordinary star of the material sector. The space-time relationship is inverted only in the translational motion of its components. In the cosmic star, on the contrary, all of the space-time relations are the inverse of those of the ordinary material star. Not only the translational motion, but also the vibrational and rotational motions of its constituent atoms, and, what is especially significant in the present connection, the effect of gravitation. Consequently, the white dwarf is an aggregate in space, and we see it as such, whereas the cosmic star is an aggregate in time, and we cannot recognize it as an aggregate. Okay, so that's a key distinction there. If you have a white dwarf star, the white dwarf star is from the material sector, and so we see it, even though we can't see time, we see the inverse in space, but it is localized in space because its atoms come from space. It's a material aggregate, but it has gained an explosive speed that has carried its motion. That explosive motion has gone out beyond the speed of light. And so we see it only in the inverse as an implosion in space. But a cosmic star is entirely in the cosmic sector. Its atoms, its molecules, and its charges, all of its constituents are in the cosmic sector, so we cannot see it as an aggregate. We see it as non-local, which means that we see it as a dispersed aggregate, or dispersed over the entirety of space. So we see it as a very low-level energy over the entire aggregate of space, which you would probably recognize as the 3-degree microwave background radiation. Okay, next paragraph. Even those contacts which do take place between matter and the individual particles of cosmic matter or antimatter that enter the local environment do not have the kind of results that are anticipated on the basis of current theory. In present-day thought, the essential difference between matter and antimatter is conceived as a charge reversal. An atom is thought to consist of a positively charged nucleus surrounded by negatively charged electrons. It is then assumed that the anti-atom has the reverse structure, a negatively charged nucleus surrounded by positively charged electrons or positrons. The further assumption then follows that an effective contact between any particle and its antiparticle would result in cancellation of all charges and reduction of both particles to radiant energy. This is a typical example of the results of the compartmental nature of present-day physical theory, which permits an assumption to be used in one field of application and a direct contradiction of that assumption to be applied in another field, both under the banner of so-called modern physics. Where the accepted theory requires that opposite charges neutralize each other on close approach, it is assumed that they do so. Where this does not fit the theory, as in the electrical explanation of the structure of matter, it is cheerfully assumed that the charges accommodate their behavior to the requirements of the theory and take up stable relative positions instead of destroying each other. In the present instance, both of these contradictory assumptions are employed at the same time. The stable charges that somehow have no effect on each other are annihilated by other charges, presumably identical in nature. Our findings are that wherever electric charges actually do exist, the opposite charges destroy each other on contact. It does not follow, however, that charge neutralization is equivalent to annihilation. In actual practice, only one of the reactions between particles and what are presumed to be antiparticles follows the theoretical scenario of annihilation. The electron and positron do, in fact, annihilate each other on contact with the production of oppositely directed photons. The antiparticle of the photon, in the accepted sense of the term, a particle equivalent to the proton in all observable respects, except that it is negatively charged, has been detected. But contact of this proton proton, not photon. Yes, okay, I'm sorry. The antiparticle of the proton, in the accepted sense of the term, a particle equivalent to the proton in all observable respects, except that it is negatively charged, has been detected. But contact of this antiproton with a proton does not result in annihilation of the particles into radiant energy. Here, the situation is not as straightforward as in the annihilation of the electron-positron pair, report Bourse and Matz. And indeed, it is not. The interaction of these particles produces an assortment of transient and stable particles not essentially different from those which appear in other high energy interactions. As these authors say, different kinds of mesons are released in the process. In the light of our new findings, it is evident that these are not annihilation reactions. They are cosmic atom building reactions. We will examine the nature and characteristics of such reactions in chapter 16. Okay, let's try one. No, I guess that probably is enough for today. Now this is, you know, difficult, again, material. We're talking about something pretty abstract when we're going into the cosmic sector. But just recall that the cosmic sector is a mirror image or the same as what's going on in the material sector, at least on the broad scope. And you know, so you're not necessarily on totally unfamiliar ground. Okay, we will take over tomorrow here with this next paragraph, and thanks for tuning in. Have a great day.